Hey folks, in this video, we'll take a closer look at the overall architecture of Amazon EKS and explore how pods get their IP addresses using the VPC CNI plugin. We'll break down the different modes available and help you understand when and why you might use each one. Here's what we'll cover in this video. First, we'll start with a high-level overview of the overall EKS architecture. Then, we'll dive into the secondary IP mode, which is the default mode for the VPC CNI plugin. After that, we'll explore prefix mode and talk about its benefits. Finally, we'll look at custom networking. For each of these modes, we'll show a demo to help you see how it works in practice. Amazon EKS is a managed Kubernetes service, meaning AWS manages the control plane aspects on your behalf, so you don't have to worry about its operation or maintenance. Your responsibility primarily lies with managing the worker nodes. As shown in the diagram, the control plane runs in a dedicated AWS management account outside of the customer's direct control. The worker nodes, however, run within your AWS account. For worker nodes to join the cluster, they must communicate securely with the Kubernetes control plane. To facilitate this, AWS creates control plane ENIs in your account which enable the communication between the control plane and your worker nodes. Additionally, the worker nodes need access to AWS services for tasks such as pulling container images from Amazon ECR, managing EBS volumes via EC2 APIs, sending logs to CloudWatch, and applying patches or updates. This access typically happens via VPC endpoints or through a NAT gateway, since it is best practice to keep your worker nodes in private subnets to enhance security and reduce exposure to the public internet. Secondary IP is the default mode for VPC CNI. The ENI, just like any other EC2 instances ENI, has a primary IP address. AWS node is a daemon set that runs on each worker node and manages all networking aspects on the worker node, from IP address allocation to attaching and detaching additional ENIs to the node to NAT behavior and much more. In this mode, the ENI, in addition to the primary address, has a number of secondary addresses. When a pod, Nginx in our diagram, comes online, AWS node ensures one of the secondary addresses is allocated to it. Once the address is allocated to Nginx, CNI, the VPC CNI, notices its warm or unused pool has become less and reacts by adding a second ENI, which again will have a primary address and a number of secondary addresses. Let's lab it up together and see how it works. Let's start by looking at the nodes. Then focus on the pods running on the node with IP 10.1.130.86. Notice that some pods are running with the node's primary IP address. These pods are using host networking, which means they share the node's IP address. Now, let's check the elastic network interfaces or ENIs attached to the worker node 10.1.130.86. You can see one ENI with the primary IP 10.1.130.86, and it has 5 secondary IP addresses assigned. Let's now create an Nginx deployment running the Nginx image with 2 replicas. Each pod lands on a different node. Again, our focus is on node 10.1.130.86. We can see that the IP address of the pod here, 10.1.141.139, matches one of the secondary IP addresses assigned to the ENI. Since we have now used one of the secondary IPs, the VPC CNI, running as the AWS node pod, if you recall, attaches a new ENI to the node from the same subnet. This new ENI again has its own primary IP, 10.1.143.1, and 5 secondary IP addresses similar to the first ENI. Next, let's check the number of pods running in the default namespace. We scale our deployment to 5 pods. Three of those pods, as you can see, are now on the node 10.1.130.86. Their IP addresses 10.1.129.193, 10.1.135.247, and 10.1.129.34 match the secondary IPs on the first ENI. At this point, we still have only 2 ENIs attached, and the second ENI's secondary IPs are still unused. We then scale the deployment to 8 pods and check the pod distribution again. We can see 4 pods running on 10.1.130.86. Running a command to filter pods by the node confirms that there are 4 pods. Scaling up further to 10 replicas, we see 5 pods on 10.1.130.86, meaning the first ENI's secondary IP addresses are fully used, but the second ENI's secondary IPs are still unused. Finally, we scale the deployment to 12 replicas. Now, 7 pods run on 10.1.130.86, which shows that we exhausted all 5 secondary IPs on the first ENI and have started using 2 secondary IPs from the second ENI. Looking again at the ENIs attached to 10.1.130.86, we see that because the second ENI's IPs are being used, the VPC CNI reacts by attaching a third ENI to the instance to provide more IP addresses. Prefix mode is an IP allocation strategy used by the VPC CNI plugin that helps increase the number of pods you can run on each node, also referred to as the pod density. Compared to the traditional secondary IP mode, Prefix mode also reduces the number of API calls needed to manage IP addresses, making it more efficient. Keep in mind though that the total number of pods on a single node depends not only on networking, but also on the compute capacity of the node itself, like CPU and memory resources. In prefix mode, each ENI still has a primary IP address, but instead of assigning individual secondary IPs, AWS assigns a /28 prefix to the ENI. This gives the ENI 16 usable IP addresses per prefix, allowing you to run more pods per ENI compared to secondary IP mode. To enable prefix mode in Amazon EKS, you just need to set the Enable Prefix Delegation environment variable in the AWS node daemon set. This tells the VPC CNI plugin to start assigning IPs using prefixes instead of individual secondary IP addresses. In this example, we're using a T3.medium instance to show the difference in pod density between secondary IP mode and prefix delegation mode, purely from a networking perspective. In both cases, the instance supports up to 3 ENIs. In secondary mode, each ENI can have up to 5 secondary IP addresses. Following the formula on the screen, the T3.medium can support up to 17 pods using the secondary IP mode. Now in prefix mode, each ENI can have 5 prefixes, and each prefix is a /28, which gives 16 usable IP addresses per prefix. That means 5 times 16 is 80 pods per ENI, and with 3 ENIs, that is 80 times 3, which is 240 pods total from a networking standpoint. Of course, in practice, a T3.medium does not have enough CPU or memory to run 240 pods. But this highlights how prefix mode greatly improves pod density by removing IP limitations even on smaller instances. The MaxPods tool is a script provided by AWS that helps calculate the maximum number of pods you can run on an EC2 instance, both in secondary IP mode and prefix mode. It takes into account both networking limits and the instance's compute capacity. Let's run the script for a T3.medium instance and a specific version of the VPC CNI. With prefix delegation disabled, the script reports a maximum of 17 pods, which matches our earlier calculation based on secondary IP mode. Now, we run the same script again, this time with prefix delegation enabled. The result is 110 pods. That's a significant jump in pod density from a networking standpoint. But here's the key point. The script does not just rely on IP address availability, it also considers the instance's CPU and memory limits. So even though prefix mode would allow 240 pods from a pure IP perspective, the MaxPods tool caps it at 110 for a T3.medium because that is the realistic limit based on compute resources. Let's take another look at our EKS worker nodes. First, we'll check how the VPC CNI plugin, specifically the AWS node daemon set, is configured for prefix delegation mode. To enable prefix mode, we need to set the environment variable enable prefix delegation to true. 2 additional environment variables play a key role in how IPs are managed. The warm ENI target, this ensures the CNI always try to keep a number of unused ENIs available. The warm prefix target, this ensures that if an ENI can hold more prefixes, the plugin keeps a number of unused prefixes available. If all prefixes are used up on an ENI, the CNI will allocate a new ENI if the instance supports it. Now, let's look at the pods running on node 10.1.144.134. Most of the pods are using host networking, which means they are sharing the node's primary IP. But take a look at these three pods: 10.1.154.128, 10.1.154.129, and 10.1.154.130. These are using IPs from a prefix assigned to the ENI. Given that the warm prefix target is set to 1, the VPC CNI will keep one additional prefix ready in case the current one gets used up. Looking at the ENIs attached to this node, we see the primary IP 10.1.144.134 and 2/28 prefixes assigned. When we check the pods again, we can confirm those three pods, IPs .128.129.130, are from the prefix 10.1.154.128/28. Now, let's scale our Nginx deployment. Previously, we scaled it down to 0. Now we scale it up to 24 replicas. And confirm that all pods are running. Next, we check how many of those Nginx pods are running on node 10.1.144.134, and specifically, how many are not using the host IP. These are the ones that consume IPs from the prefix pool. We count 15 pods using prefix assigned IPs. Since a /28 prefix provides 16 usable IPs, that means we still have not fully exhausted the first prefix, so the CNI does not need to assign a new one yet. Next, we scale to 26 replicas and again check the pod distribution. Now we find 16 pods on the node, meaning we've used the full 16 IPs from the first prefix. Still, because we have a second prefix already available and unused, the CNI does not allocate a new prefix yet. Finally, we scale the deployment to 28 replicas. This time, we find 17 pods on the node using non-host IPs. That means we've fully utilized one prefix and started using the second. Since we no longer have a warm prefix available, the CNI reacts by provisioning a third prefix and attaching it to the same ENI. Looking at the ENI ending in 4170, we now can see 3/28 prefixes attached: the 10.1.151.80/28, the 10.1.154.128/28, and the newly added 10.1.154.224/28. This confirms that the CNI is correctly maintaining the warm prefix pool as configured. Custom networking in Amazon EKS allows you to assign pod IPs from a different subnet than the one used by your node's primary network interface. This is especially useful when your VPC's primary CIDR range is running low on IP addresses. You can simply use a secondary CIDR block for pod networking. But it's not just about IP exhaustion. Another important use case is separating node and pod traffic. For example, using different routing rules or security groups to isolate pod-level traffic from node-level traffic. The VPC CNI plugin handles this by using the ENI config custom resource definition, or CRD. This tells the CNI which subnet and security group to use when creating ENIs for the pods. In this diagram, you can see a worker node with its primary network interface ENI1 attached. Notice that ENI1 does not have any prefixes or secondary IP addresses assigned to it. That's because the VPC CNI plugin, using the configuration defined in the ENI config CRD, has determined that it should use a separate ENI for pod networking. As a result, it creates ENI2, which is specifically used for assigning IP addresses to pods. In this example, we are simulating a scenario where the VPC's primary CIDR range is running low on available IPs. To solve this, a secondary CIDR block from the range 100.64.0.0/10 has been added to the VPC. The CNI uses this secondary range to allocate IPs for pods through ENI2. Continuing with the same approach, we start by looking at the nodes. Then we review the VPC CNI settings required to enable custom networking. To enable custom networking, you just need to set the environment variable custom_network_CFG equals true in the AWS node daemon set. In this lab, I'm also using prefix delegation mode, but that's optional. Now, let's talk about how the CNI knows which subnets and security groups to use for pod networking. That's where ENI config comes in. Think of the ENI config CRD as a mapping between nodes and the networking resources they should use. You typically create one ENI config per availability zone. For example, let's say we have two worker nodes, one in US East 1A and one in US East 1B. Each AZ will have its own ENI config that defines the subnet and optional security groups that should be used when the CNI attaches ENIs for pods. Now, take a look at an actual ENI config object. It's named US East 1A and it's linked to a subnet in the secondary CIDR block 100.64.0.0/10. Note that EKS worker nodes are automatically labeled with topology.kubernetes.io/zone, indicating the availability zone in which the node lives. The parameter ENI config label is set to topology.kubernetes.io/zone. This means the CNI will search for ENI configs whose name matches the value of topology.kubernetes.io/zone, and in our example, this means the CNI will search for ENI configs whose name is either US East 1A or US East 1B, as our nodes live in these two availability zones. So if the node is in US East 1A, it will be automatically labeled with topology.kubernetes.io/zone equals US East 1A. The CNI will look for an ENI config with the exact same name and use its subnet and security group settings to provision a new ENI. Now, let's check what is happening on the node 10.1.147.60. First, we look at the ENIs attached to it. As expected, we see two ENIs. One is the primary node interface with IP 10.1.147.60, and the other is a pod ENI with primary IP 100.64.2.214. That pod ENI also has a prefix allocated 100.64.2.144/28. At this point, all running pods are using host networking, meaning they share the node's primary address. Now, we scale our Nginx deployment to 2 replicas. We observe that one of the Nginx pods is assigned the IP 100.64.2.144, which is part of the 100.64.2.144/28 prefix range attached to the pod ENI. Because one IP has now been used and the warm prefix target is set to maintain at least one unused prefix, the CNI provisions another /28 prefix. Looking at the ENIs again, the pod ENI now has 2 prefixes, 100.64.2.144/28 and 100.64.2.96/28. This confirms that the VPC CNI is maintaining the warm prefix pool as expected. In the next episode, we'll dive into security groups for pods, explore in-depth NAP behavior, and how to expose services outside the cluster. Thank you for watching, and see you next time.